In this lesson, we're going to look at mutually exclusive events. We've seen the sample space before. It's two six-sided dice that are rolled. We're going to consider events E, F, and D, where E is rolling a sum of 8, F is rolling a sum of 4, and D is rolling a double. So let's have a look here. It says the sample space shows the outcomes when two dice are rolled. The outcomes for event E are 6, 2, so let's see there, 6, 2, which is here, because 6 plus 2 is 8, 5 plus 3 is 8, 4 plus 4, 3 plus 5, 2 plus 6. Those are all sums of 8. Outcomes for event F, that's when we have a sum of 4. That would be 3, 1, 2, 2, and 1, 3. Outcomes of event D are rolling a double, so we would have 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. So we can see all of those events on our sample space here. Now, we say that events E and F are mutually exclusive events because they do not have any common outcomes. The events may be defined as disjoint sets because they cannot occur at the same time. Okay? So that's for events E and F. And you can see there's no overlaps between E and F. If you look down at the bottom, we can see here's events E and F, and they're drawn using a Venn diagram, and there is no overlap because these are disjoint sets. They are mutually exclusive. However, if you look at E and D, E is rolling a sum of 8, and D is rolling a double, and we do have an overlap there, the 4, 4. And you can see up here, that's where the highlighter and the green are overlapping. You can also see between the doubles and our sum of 4, those are not disjoint either because the 2, 2 also gives you a sum of 4. So when we have non-mutually exclusive events, right, the events are not disjoint because at least one outcome occurs in both events. And you can see that in the diagrams here. Alright, let's take a look at the next page. We're going to have a look at the list here. It says determine which of the following events are mutually exclusive and which ones are not. So it's a good idea to look through this and to label them independently, and then you can check back to see if your answers match mine. For number 1, attending school and having a job are not mutually exclusive because a lot of students will attend school and have a job at the same time. For number 2, being a member of the girls' basketball team and the boys' basketball team, well, you can't be a member of both at the same time, so those are mutually exclusive. Rolling a 2 and rolling a 3 on a die. On the same die, those two events cannot happen simultaneously. They're two independent events, so they're mutually exclusive. Driving a car and talking on a cell phone should be mutually exclusive. Can you do those two things at the same time? Yes, but it's unsafe. So we'll say mutually exclusive because there's a law that says you should not do that. For 5, finishing first and second in the Manitoba Marathon, well, that's mutually exclusive. Both of those things cannot happen at the same time. For 6, selecting a diamond or a jack from a deck of cards is not mutually exclusive because you can pull the jack of diamonds. Here for number 7, selecting a king or a queen from a deck of cards. Now the fact that it says or, and we're only picking a single card, you're not going to get both of those events happening. You're going to get either the king or the queen, not both. Reminder here, the addition rule for probability. The word or in probability implies addition, and the word and in probability implies multiplication. And when we're looking here for or, right, that's union. And when we're looking at and, that's going to be our intersection. So here, the formula for mutually exclusive events, the probability of A or B is the probability of A plus the probability of B. And when the events are not mutually exclusive, which means we have an overlap, we need to get rid of that overlap, the intersection, and that's represented here, because we don't want to double count those. This is called the principle of inclusion-exclusion. Let's take a look at example 1. says Yannick and Violetta are playing a board game. To move on his turn, Yannick must roll either doubles or a sum of 7 with the 2 standard dice. So we've got the sample space here. They've just colored the dice so we can tell the difference between the first dice and the second dice. And we can see that there's 36 total ways of getting a sum with 2 die. Now, I've added all those up and put them in another sample space here. It's the same one, just looking at 1 and 6 instead of writing that down, we have that that's sitting here as 7. Okay, it's kind of a flipped upside down version, but it's the same thing. The question we're being asked here, what is the probability that Yannick will move his turn? So we want to know, what is the probability of getting doubles or a sum of 7? Well, that would mean we would have to figure out the probability of doubles and add that to the probability of getting a sum of 7. Well, we can do that for sure. So looking at our chart here, doubles would be all the way down here, 2, 2, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. So I've got 6 of those. So the probability of getting doubles would be 6 out of 36. And then the probability of getting a sum of 7, I can see easier in this chart, 7's all the way down here. And that would also be 6 out of 36. So the probability of Yannick being able to move on his turn will be equal to 6 out of 36 plus 6 out of 36. The common denominator is always already there, so that's 12 out of 36. And you can reduce that if you want to 1 over 3, but you can leave it like that. So the probability that Yannick will move is equal to the probability of getting doubles or a sum of 7. Let's have a look at example 2. We're looking at the same board game that the two played, but according to a different rule, if a player rolls a sum that's greater than 8 or a multiple of 5, the player gets a bonus 100 points. Determine the probability that Violetta will receive a bonus of 100 points on her next roll. So that means we need the probability of getting a sum greater than 8 or the probability of a multiple of 5. So again, we're going to figure out the one and then the other. But we have to be careful. It's a little bit different than what we did for Yannick, because Yannick's events were mutually exclusive. There was no doubles that also gave us a sum of 7. But this isn't the case here for Violetta. It says sum greater than 8, so let's do that one first. So that would be 9 or higher. So these are all greater than 8. And then the other one is a multiple of 5. So a multiple of 5 would be 5s, or multiples of 5. 10 is also a multiple of 5. So if both of these are happening, it's one or the other. If I counted them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And you can see that there's 14. Am I double counting the 3 10s? No, I'm just counting the ones that are there. However, when we do that mathematically, we're not going to be doing that. So we need to make sure that we subtract off what we double counted. So here's what I mean. So the probability here would be the probability of getting a sum greater than 8 plus the probability of getting a multiple of 5. Now if you just did that, the sum of greater than 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The sum of multiple of 5, 1, 2, 3, 4, 5, 6, 7. that would give you 17. But that's because there are 3 values that are double counted, so you have to subtract off the probability of both, which means we would subtract off those 3 10s. Now this is probability, so it would be 10 out of 36, 7 out of 36, 3 out of 36. So you're not just counting the arrangements, but you're counting the probability that that holds true. And in this case, that would be 14 out of 36. Let's have a look at example 3. Now in example 3, you can see our Venn diagrams coming back. Why is this the case? Well, it says a school newspaper published the results of a recent survey. Are skipping breakfast and skipping lunch mutually exclusive? Determine the probability that a randomly selected student skips breakfast but not lunch, and determine the probability that a randomly selected student skips at least one of breakfast or lunch. So we're using this data here. It says the eating habits student survey results. Let's label this B for breakfast and this L for lunch. So 62% skip breakfast, 24% skip lunch, 22 eat both breakfast and lunch. Well, that's not here. This would be wrong if you put it there. The 22 belongs out here because they don't skip breakfast or lunch. They eat both breakfast and lunch. Now these are all percentages, so I'm just putting them here just so we can see what's happening. So how do I figure out what's going on? Well, if they are all percents, what do they all have to add up to? Well, they all have to add up to 100. So if I go 100 and subtract off that 22%, that means that 78% skip breakfast or lunch. Alright, well, if I take that 62% and add it to my 24%, we know that that value should be, and it is in fact, larger than 78% because we have all those students in here that are being counted more than once. So if we take that 86%, subtract off the 78%, we'll get the 8% that skip both. And once you have that 8% that skip both, you can now figure out how many skip breakfast only and how many skip lunch only. So if we take 62 minus 8%, we would get 54% that skip breakfast only, and if we take our 24, subtract 8%, we'll get the 16% that skip lunch only. Alright, answering the question that they're asked, I filled out the Venn diagram, but what are they asking? A. Are skipping breakfast and skipping lunch mutually exclusive events? No, because 8% skip both. B. Determine the probability that a randomly selected student skips breakfast but not lunch. That would be that 54%. And C, determine the probability that a randomly selected student skips at least one of breakfast or lunch. And that would be the 78% that we figured out right at the beginning up here. Because that would be all of this, right? 54 plus 8 plus 16. All right, have a look at example 4. It says Reed's mother buys a new washer and dryer set for $2,500 with a 1-year warranty. She can buy a 3-year extended warranty for $450. Reed researches the repair statistics for the washer and dryer sets and finds the data in the table below. Should Reed's mother buy the extended warranty? Justify your decision. So let's fill out the Venn diagram according to the information, and then let's draw some conclusions. So here's the probability, the repair with an extended warranty period. So 22% is for the washer, so we're looking at just the washer. And then our dryer is 13%. And for both, it's 3%. Now, there is some overlap here, so in order to figure that out, we would take our 22% minus our 3% to give me 19% for the washer only, and 13% minus 3% to give me 10% for the dryer only. So what's the probability that at least one of them needs repair? Remember that at least one probability? Well, first of all, I'm going to put in these values, so it's going to bother me. Well, the probability of at least one would be 19 plus 3 plus 10%. So let's write that one down. So 19 plus 3 plus 10, and that would give us 32%. Now the conclusions you draw from this are pretty personal. Now, if you really depend on that washer and dryer, 32% might seem like a lot. And then for some people, 32% might sound like, well, that's not a really huge chance that at least one of them is going to need repair. So I might choose not to buy the extended warranty. So as long as your answer is based on the results that you're getting, it's a bit of a personal preference. So there is a 32% chance that repair is needed. I believe this is low, so I wouldn't buy the warranty. A lot of people have different opinions on extended warranties and warranties anyways, but what we're talking about here is based on the results and the research that was made. Alright, last example. A car manufacturer keeps a database of all the cars that are available for sale at all the dealerships in Western Canada. For Model A, the database reports that 43% have heated leather seats, 36% have a sunroof, 49% have neither. Determine the probability of a Model A car at a dealership having both heated leather seats and a sunroof. Okay, so I'm going to do leather seats here and a sunroof here. We're given that 43% have heated leather seats and 36% have a sunroof. We want to know how many have both. So in order to know that, how can I figure out the other information? Well, 43% plus 36% is 79%, right? But the total here, when you add everything up, should give us 100%. So 100% minus 79% gives us 51%. Okay, so 51%. So if I take that 79 minus 51, I'll get that overlap of 28% difference. So 28% of the cars will have both leather seats and a sunroof. If you want, you can finish up the Venn diagram and you'll get 15% for leather seats only and 8% for a sunroof only. Depending on what the question was being asked, you might need that other data. But in this case, they just wanted to know the probability of Model A car at a dealership having both, and that would be 28%. If you look at the last page of this section, we've got a really nice summary of mutually exclusive events and non-mutually exclusive events, and those formulas there as well. So it's a really good idea to have a look at that. It might be something that you can put on your cheat sheet to help you with your test. Thanks for joining me in today's lesson.